Hello, today we want to talk about parallel AC circuits. Before, we have learned that AC circuits in series have different types of configurations, such as RLC or RL, RC, and you can have multiple um, permutations between the elements that you place in series. We've learned how to compute the reactance of the circuit in series and the impedance of the total circuit or the total impedance. Now we want to do the same thing but with elements in parallel. The objectives are to become familiar with the characteristics of parallel AC networks, be able to find the total impedance of circuits in parallel, use the Kirchhoff's law to find the current through the branches of the circuit, and keep using the divider rule to find the quantities within the circuit. So, just like elements in series, circuits with elements in parallel can be computed to get the total impedance by using the laws of parallel circuits. In other words, the reactance because of the resistor is going to be the same. The reactance of the capacitor is going to be still computed the same, 1 over 2 pi C times frequency, and the reactance of the inductor is still going to be the same. So the elements by themselves still have the same way of computing the reactance. That does not change. What it does change is the way to compute the total impedance. Before, it was just a summation. When we did series or circuit in series, we would do a summation of the reactances for each element. Now we're going to do the computation of elements in parallel, which is 1 over each reactance. So in that case, what we need to do is use this formula of total impedance, which is 1 over, again, 1 over each impedance. And since for total impedance, almost every time we want to do the magnitude, then instead of impedance, we use reactance. Because remember, the difference between impedance and reactance is the impedance is taking into consideration the angle shift or the phase shift. For reactance, it's only the magnitude of the resistance. So the total impedance will have a magnitude and a phase shift. So we'll see that in examples right here. So the case of um, RL circuit in parallel, the resistor and the inductor are in parallel. In this particular case, they told us that the reactance of the inductor is 10. Therefore, they already computed 2 pi FL. They didn't give us the number or the value of the inductor. They gave us the reactance already. So it's very simple because we know that the resistor has 0 phase shift, but the inductor has a 90 degrees phase shift. In order to compute the total impedance of these RL circuit in parallel, we can use this formula, which is basically we know that from circuits in parallel, we have 1 over Z equals, or basically voltage over impedance equals the voltage over the resistor and the voltage divided by um, the inductor. So voltage is going to cancel, and this is basically the formula that we had before, which is 1 over the impedance equals 1 over the reactance plus 1 over the reactance of the inductor. Now, from here, you get this part. If you keep getting the um, this is the actual impedance. If you do the computational the manipulations between the denominator and denominator to get the total impedance, you'll get to this point when there's only two elements. Another way to compute, well, but the other thing that you can do is if this is the impedance, but since we have the reactance, another way that we can do, which I like a lot because it's straightforward just by using calculator, is that you get your still one, and then we compute the impedance of each element. So 1 over the impedance of the resistor plus 1 over the impedance of the inductor. Now we're computing the total contribution of the impedance because of the reactance. And this is, if we use the calculator, we say 1 over square root. I think you should do this in your calculator so you know how to compute this stuff. 1 over square root of 1 over 10 squared plus 1 over 20 squared. If you do that, that will give you 8.94. So this is equal to 8.94 ohms, which is pretty much what we got here. Except for this part is easy to compute the impedance, but if the question is for impedance and the phase shift, then it's just straightforward. You use this guy right here, which you know that this will be nothing but 20 times 10 is going to be 200 at an angle of 0 plus 90 is 90, divided by square root of 20 squared plus 10 squared, and that will give you 200 divided by square root of 20 squared plus 10 squared, and that gives you 8.94. So it's the same thing. That will give you 8.94. And in this particular case, it's going to be straightforward because you know that this one has at the angle of 90 because of the inductor, and here you have the angle of, let's see, 10 is going to be y divided x, so 10 divided 20, and tangent inverse of this is 26.56. So this part right here, let me write down again, this part right here is using the calculator, I do square root of 20 squared plus 10 squared, and that will give me 22.36 at an angle of 26.56 to 6.56. Okay, now evidently that divided this number is going to be 8.93, and then 90 minus 26.56 is 63.43. So this is how you get this value. You would do 200 divided by, so this number right here, just to show you how to do it again, it will be 20 times 10 is 200, and since it's multiplying, it's going to be 0 plus 90, 90, divided by square root of 10 plus square root of 20, that was 22.36 at an angle of 26.56. You know that that and this will give you 8.94, and the angle is 90 minus 26.56, which is equal to 63.43. 0.43. So those are the two things that you can do. Just if you just need the impedance, the total impedance to compute the voltage and the current, you go this route. Or if you know the phase, if you want, also you can go this route because it's easier to get the phase shift right away. So the other concept that we will learn is that we already know the term reactance and we know the term impedance. Well, 1 over reactance is called electrical susceptibility, and 1 over impedance is called admittance. So the this is similar to conductivity. If you remember from DC circuits, 1 over resistance is conductance. Similarly, in AC circuits, 1 over, or the inverse of the impedance is admittance. Okay, so if you have a circuit in parallel where you have two elements, this could be a resistor and an inductor, etc., whatever it is. If it's a capacitor, you just find the reactance of the capacitor and the impedance. The key is to know that given the total impedance, which we know how to do, at this particular point we don't care about the phase shift because we just want to know the current, which is on the real axis, the current, the total current. This particular case, we know that the total impedance is simply using your calculator 1 over xz1 is going to be 1 over the reactance of the first element, if it's a resistor, a capacitor, inductor, whatever it is, squared plus 1 over the reactance of the second element squared. That will give you the total impedance, which you will later use to compute your current given the initial voltage. Okay, 10 volts, 120 volts, wherever it is. Now, since you know that in parallel from DC circuits, you know in parallel the voltage through each branch is the same. So V1 equals V2. So what we do now is compute the currents through each branch, which is not going to be the same. And we do that with simply doing the voltage, which is the same, through the impedance or the reactance of the first element. Okay, so the symbol for admittance is Y, and it's simply saying that voltage over impedance is the same as voltage times admittance. Okay, so that's how we get the current through branch 1. The current through branch 2 is going to be the voltage divided by the impedance squared. Okay, how do you get this impedance? Well, it's very easy. It's the reactance at a phase shift. Whatever this is, resistance, inductance, capacitance, you know that if it's a resistance, it's simply the value of the resistor. If it's an inductor, it's 2 pi frequency times inductance. If it's capacitance, it's 1 over 2 pi frequency times capacitance. Okay, so since the current for this particular case doesn't ask for the phase shift, you simply find the total impedance if you need to find the total current, and then for each reactance you can get the impedance from that reactance, and you can compute the current through each branch. So for example, they give us the voltage at omega t, which is 2 pi ft, and a phase shift of 53 degrees, and we want to know what's the power, the total power, and we want to know what is the current through the resistor and what is the current through the inductor. Okay, so for that we do the same thing. We find the total impedance, which is 1 over square root of 1 over the reactance because of the resistor plus 1 over the reactance because of the inductor. We already know how much is the reactance because of the inductor. It's 2.5. If not, we will just simply do 2 pi f times L, and we know that the total impedance is 1 0.99 ohms. If they were asking about the total admittance, we simply have to do 1 over 1.99, which is 1 divided 1.99, 0.02, 0.502 cents. Okay. But they're not asking about the impedance in this particular case, about the admittance. They're just asking what is the total power and what is the current through each leg. We know that the total power is the voltage times the total current times the, well, actually, remember, this is the RMS voltage times the RMS current, times the cosine of the angle between the resistor and the imaginary reactance or capacitance or impedance. Okay, so in this particular case, we don't have a capacitor, so we know that the impedance is going to be positive because of the inductor. So what we need to do is find the angle because of the total impedance. This angle will help us find the total power. All right, so what we do next is we find the total current because of the total impedance, and we simply say that V divided the reactance is equal to 20 divided by 1.99, or basically 2 ohms, is equal or very close to 10 amps. So this current right here, this one is 10 amps, or very close to 10 amps. Then we know that the voltage is the same through each branch. We just simply want to find the current through each branch. And for that, we do the voltage divided by the reactance of the resistor. We know that it's going to be 20 divided by 3.33, 6 amps. And the current through the inductor is the voltage divided the reactance because of the inductor, and that is 20 divided by 2.5 is 8 amps. Okay, notice that if you do I total or IR plus IL, is not going to give you 10 amps, right? So it's not like in DC circuits where you have your Kirchhoff law where the summation of IR plus IL will give you the total current. In AC circuits, it's not like that because there's some part of this current that is going to the magnetic domain. So in that particular case, what we need to do is find, if you want to get the total current, you'll have to do, let me do a calculator to double check that we're getting those values. So 8 squared plus 6 squared square root of that, 10, correct, yes. So in order to get this total current, you have to find the total magnitude, which is IR squared plus IL squared. So if you do 6 squared, will be 36, and if you do 8 squared, will be 64, and 36 plus 64 is 100, square root of 100 is 10. So this is because, as we said before, this applies for the current as well. You get the real contribution of the current through the capacitor, through the resistor, and an imaginary contribution of the current through the inductor. This total current is the actual current coming from the source, which is 10 amps. So this value here, this vector, is 10, and it's computed like this. So in AC circuits, you do not get your total circuit, your total current by adding the current through each leg, because it is not a real contribution from the inductor and the capacitors. What you need to do is find the total current by applying the magnitude or the Pythagoras theorem, because it's contribution in the x, y, and z plane, where you have R squared, or the current through the resistor, plus the current through the inductor. Very quickly, if you were to have a capacitor, you'll do the same thing. You'll find IC equals voltage divided by the reactance through the capacitance. And what you would have to do is say that I, the current, the total current, equals the real contribution still is the same, plus the contribution of the inductor minus the contribution because of the capacitor, because it's storing, the capacitor is going to store charge, and then squared. Okay, so this is if you have a capacitor. It's always like this. This is how you find the total current. All right, so we have the total current, which is 10, and we have the current through each leg, which is 6 and 8 amps. And they want us to find the total power. Okay, so the total power is very simple. We're gonna have the RMS voltage, which in this case will it's right here, square root of 20. So in this particular case, we just get rid of the square root and we have 20. And the voltage is going, this is the RMS current, 10 amps. So the total power is 20 volts times 10 amps times the cosine of the angle. How do you find the angle? You know that the angle is going to be the tangent of your y contribution, your imaginary contribution, divided by your real contribution. So tangent inverse of 8 divided by 6. This is 53 degrees. So the total power is 20 times 10 times cosine of 53, and that gives you 120 volts.